We're coming. Okay, so this is Charles Yang is going to be speaking now on the third day of the summer school on understanding LLM understanding. He's professor of linguistics and computer science and director of the cognitive science program at University of Pennsylvania. His research concerns language and cognitive development, which is what we've been discussing mostly, not entirely for the first few days. Soon it'll be transitioning to more to wider horizons. From a computational perspective, his book, The Price of Linguistic Productivity, won the Leonard Bloomfield Award from the Linguistic Society of America. And I now pass the equal to Charles. Welcome.
Thank you. It's a good thing you mentioned the heritage of Chomsky and University of Pennsylvania, because that's what I intend to go back to today, and maybe to look at what's been happening in the past 70, 80 years, in particular in the past 10 years, having to do with LLM and how that relates to a much longer intellectual tradition. Because if you think about it, the original end-to-end systems were proposed here at the University of Pennsylvania in the form of two scholars, Zadig Harris and his student Noam Chomsky. For those of you who know the history, this will be a review. But what Chomsky set out to do in his dissertation, heavily influenced by Harris and also Goodman and Quine and so on, was very much a logical positivist program, because he was interested in what comes known as a discovery procedure. The discovery procedure is you take a corpus and you're supposed to create the phonemes, the morphemes, the syntax, and the morphology, and so on. An outcome of the corpus will be a grammar. This is from syntactic structure. The theory must provide a practical and mechanical method for actually constructing the grammar, given a corpus of utterances. Can you hear me okay?
Yes, it's fine.
Okay, good. And he said this has to be practical and mechanical, and it really goes without saying it has to be interpretable, because in the end you come up with a grammar. So people are talking about end-to-end systems these days, but I think this is actually the first and original end-to-end proposal. The problem was that it was actually premature, and for many reasons. For example, when Chomsky did his work, there was no corpus. The Brown corpus was still about 10 years away. This is the first publicly, generally available corpus of any language at scale. There's really no theory of learning or computation, really. Certainly, there's probably no theory of programming languages yet. And there was virtually no understanding of child language, because the most famous study in child language acquisition, namely the WUC test, was done a year after syntactic structure. So as a result, and Chomsky tried his hand at the discovery procedure in his thesis, The Logical Structure of Linguistic Theory. He really didn't get very far. So as a result, the field, I think, changes orientation and moved on to what's called an evaluation procedure, which is much more familiar to linguists, and probably to people outside of linguistics, which is if you're given a corpus, you're given two grammars. You don't care where those two grammars come from. Your job is to decide which is the better grammar. Okay, so as a consequence of the discovery of the shift to evaluation procedure, most linguists, at least in general grammar tradition, has been busy mapping out the totality of grammatical space, so that all the child has to do is to pick and choose. But the question we have to ask ourselves is that, does it actually help? Many of us spend many years trying to, on the one hand, work out the space of possible grammars, on the other, devising algorithms to learn the grammar appropriately. We ran into all kinds of problems. Because, this is not a time to go into that here, but because once you assume the learner has access to many more grammars than they actually learn, the non-target grammars have to be rejected. It's by no means easy. It's actually very, very difficult. And the other thing is that how much nativism are we willing to put up with? If all the possible grammatical forms are somehow baked in universal grammar. But I think most importantly, there was this conception that the grammar you have to learn must be the best grammar given a corpus. And Chomsky was fully aware that this is not in general practical, because I won't go into the details here. Being his master's thesis, he was trying to come up with a sequence of statements such that this gives the best description of the data in modern Hebrew. But the problem is that if you have n statements, if you arrange them in the sequence, there are really n factorial possibilities. You can't possibly enumerate all of them. So what he did was he sort of cheated. He only looking at the most adjacent pairs of statements, and say he found that if you swap the order, it got worse, and so therefore he was able to come up with a locally best grammar. But this discussion, I think, was basically forgotten. Most linguists have been busy mapping out the totality of UG. So this was 1955. And there was also a very important event happening in that year. That is Herb Simon's work, Satisficing. This is probably something known to a lot of people, the notion of bounded rationality, where he found, in contrast to the dominant view in economics, where we're talking about, economic agents being agents of rationality. Simon noticed, of course, later he won the Nobel Prize for it, that in many cases, humans are not doing the best possible for many reasons. Maybe they don't have the information, complete information. Maybe they don't have the computational resources. In some cases, maybe they didn't even try to get the optimal solution. So this is this is notion of bounded rationality. We can go on and on about it. We'd be happy to come back to this notion later on. This view has been very influential, but only in certain circles. In my understanding, my son is economist. This has not taken over the rationality agenda in major schools of thought in economics. And likewise, it hasn't really panned out perfectly for learning sciences either. So here I'm giving you an example. Well, this is the most influential AI textbook by far, by Russell and Norvig. And this is from the concluding chapter when they ask themselves or the reader, are we going in the right direction? And so they ask rhetorically. In chapter 1, we said our goal was to build agents that act rationally. We also said achieving perfect rationality is not feasible, okay? But for the rest of the book, they did explore this working hypothesis. The perfect rationality is a good starting point. Here's where Simon's notion came up. The notion of bounded rationality came up. And for Simon, he suggested bounded rationality works by satisficing, namely by deliberately only not enough to come up with a solution is good enough. And here's the thing I wanted to highlight in red. It appears to be a useful model of human behaviors in many cases, but it's not a formal specification for intelligent agents. However, because the definition of good enough is never given by theory, it's not made precise. If you're not made precise, machine learning people, economists can't work with it, right? Even though we know from numerous studies that humans are not optimizing for the best thing possible. So I would like to, on the one hand, go back to abandon the evaluation procedure, go back to the original end-to-end system, namely to try hard to come up with a discovery procedure. One can argue LLM are doing some kind of discovery procedure because it does operate from a corpus and comes up with something. It's generally not interpretable, but it's something. But I wanted to connect that tradition with this one. I think if you want to search for the best grammar, you are doomed to fail. What we need to do is to come up with a theory of satisficing in a precise way, and that's what's on offer, and we'll see how it goes. I'll try to limit my talk to maybe 40 to 50 minutes and leave plenty of time for discussion, because I think there's going to be some ideas here that may not be very familiar to most attendees of this event. Okay, if you think about language learning, you're learning a rule based on a set of rules based on the data. If you think about it for 2 minutes, you realize that language learning must be satisficing, because almost nothing in language works perfectly. Linguists have a fine way of saying this, namely all grammars leak. And this is well before Chomsky. The point is that if you look at the grammars of languages, they're almost always laden with exceptions. Nevertheless, in most cases, the grammar is still good enough such that we use them and we generalize them. The most famous case is probably English past tense. So English has about, depending on how you count, maybe 150 irregular verbs in regular circulation that do not add ed. But children typically learn a rule of adding ed around age 3, some earlier, some later. And we certainly do not hesitate applying to the word, the rule ed, even though it doesn't work for lots of actually highly frequent verbs in our language when we see a new verb. For example, when Google was a new verb back in the 90s, people immediately inflected the past tense with Googled. If I make up a verb, blick, you immediately say it's blicked. So if you look at it across language, you see language has many, many rules, almost none of which is perfect. Another famous case in language acquisition, I think there are German speakers here maybe, is that in German there are, to form a plural of a noun, there are 5 endings. You can add n, you can add nothing. You can like sheep. You can add er, you can add just e, or you can add s. So s in particular is only covers about 5% of the nouns in German, but it's still productive in the sense that if you new words into the language are frequently inflected with s, for example, iPhone, iPhones. If you really work out the rules of German plurals, it's complicated. Okay, I'm going to give you a list of rules here. This is on the one hand, what you will find in a typical German grammar book. On the other, this is actually the list of rules our learning model can discover automatically. I'll come back to this briefly later on. You find that you have a cascade of rules, but almost all of them have exceptions. So overall, about 15% of the nouns in German require absolute memorization. But over 80% of them are actually predictable. So even though none of the rules is perfect, all of the rules are actually good enough to be used. This is one thing to appreciate, and this is I think is well appreciated in the study of language acquisition, and people have tried very hard to tackle the problem. But there's an even stronger case for the notion of satisficing. This is where we really find divergence between human behavior and machine learning models, including large language models. So because sometimes the rules are actually not good enough. So as a result, you do not generalize. What do? You simply memorize when a novel instance occurs, you don't do anything. Right, so I'll give you many examples here. I can even go into Hungarian because it's just the same problem and the complexity there is to the other extreme. So if I say I stride down the street, you strode down the street. So stride of the verb is irregular, so it's past tense is strode. How do you say it's past participle? They have what? For almost all speakers of varieties of English I'm aware of, we don't have a form for the past participle stride. They have stridden down the street, they have strided down the street, they have strode down the street. It's not acceptable by anyone. Such cases of rule breakdown is very common in all languages. Here's another example from English. So in English, we say do, do not, don't, and are not, aren't, is not, isn't, does not, doesn't, but we don't say am not, amn't. We don't say may, meant. Even though vast majority of those auxiliary verbs in the English language does contract ent to come up as almost as if you're saying this in one word. Since in Spanish, in the third conjugation, there are many words. For example, I don't know Spanish. It's just data taken from other people. If you know French, you can probably see some cognates here. As you can say, submerge, being all the present and in present, indicative or subjunctive. You can have all the person number combinations. But for attack, you can't do that. It's known as a defective verb. Now, since we're in Montreal, and again, I don't speak French, but this is taken from published literature. Apparently, in French, you cannot say, you can say I fry, you fried, you singular, he fries, but you cannot say we fry or you plural fry and they fry. And I close, you close, he closes, but you can't say we close or you plural close, but you can say they plural, close. Am I right?
Yes, yes.
Okay, so why is that? If you make a list of those forms, one of them is going to be most dominant. Why don't you use that one? These are really legions, right? So for example, this is a famous case in Russian. In the second conjugation of Russian verbs with the dental stem, for linguistic details, I won't go into there. You can't produce the first person singular present tense form. So you can't say I conquer, I climb, I talk rudely, I stir up, or behave foolishly, and so on. It's about 60 verbs of this sort. We'll come back to this momentarily. And since Virginia was talking about determinants, yesterday, even determinants have some oddities. So you can say the Bronx and the Hague. This is only two place names I know that take the, but you can't say the Berlin, the Chicago, the Montreal. And syntax is not, spared. For example, English is about a few hundred verbs that can take a finite complement clause. So you can see John saw Bill ate pizza. John complained that Bill ate pizza. John quipped that Bill ate pizza. But only C allows the movement of pizza to the beginning of a sentence. So what did John see that Bill ate is fine, but complain and quip is not so good. Okay, so this is a case of satisficing, because in those cases, the grammar is not good enough. So all we can do is to memorize the input and do not generalize, and try to do that on the machine learning model. So these are kind of questions that concern me for many years. And these are things I started thinking about in graduate school, because these linguistic problems are fairly well known. It's been in the literature for decades. So what kind of machine learning system can solve these problems for the learner? Namely, you generalize when it's good enough, but you do not generalize when it's not good enough. I looked left and right, up and down. Most models in psychology and cognitive science, if not all, are laden with hyperparameters. You tune them to get the data to fit. So it's not clear these are actually learning models for the data or from the data, or just models that summarize the data or experimental results. Also looking at models in AI, machine learning, NLP. This is statistical NLP back in the 1990s. But almost all of the models are maximized, not satisficing. In addition to having many, hyperparameters, I won't go into details here. A lot of this developmental work was done by Virginia and others back in the 80s and 90s, with many cases where some very frequently used forms in language are learned very late. At the same time, some very infrequent and absent forms in adult input language are used robustly by children. You really have this disconnect between what the machine learning models can deliver on the one hand and what's the empirical landscape. Both if you look at phenomena across languages, as the cases I was showing earlier, when the best rule does not generalize, as well as the developmental trajectory of children's of language acquisition. So, what about large language models? I won't spend too much time on this. I think this topic came up yesterday. I'm glad Ava agreed, with me, because I think it's a little bit of overestimation of their capacities when it comes to proper linguistic tests, even if you take very large language models, right? So my former student, Jordan Connor at Stony Brook, and his colleagues, including me, have done lots of work to show that demonstrably wrong baseline models can pass those tests. Just to give you one example, there's a lot of studies try to claim that large language models have solved the problem of subject-verb agreement. As you probably know, you can have a subject with many intervening words in between, and then the verb has to agree with the subject in person. In number, in English. But if you look at the benchmark test, every single subject is actually the first noun. So all the learning the model needs to do is to agree with the first noun, not even try something simple as, in the forest, the elephants are running wild and so on, right? So I think as Ava was saying yesterday, there's really the rigor has to be raised. But I won't spend so much time bashing language models, because that's not the point here. The point is to do something better. And the other thing is that how do you not get a language model not to produce anything? As I mentioned earlier, if you train a model on French, it should not produce, they fry. They should not produce, you plural clothes, right? But how do you get a model not to produce anything? Because at the end of the day, one of the forms is going to be ranked highest by most probable, or however you want to, or least surprised, however you want to measure its goodness. So this can lead to different kind of hallucination. So here's a student work by a former student of mine, Dennis Bezer. So we took this, he trained RNA and also transformer on actually attested Russian verbs, namely the verbs that are not gapped, namely not the verbs on these on the left where the first person present tense doesn't exist. So he trained it on basically the input to a typical Russian learner. But then he fed into the model dental stems in the second conjugation. So here it is actually producing some forms, but these should be zero because a Russian speaker would not produce a form in those cases. And these are some of the forms that RNN and transformer produced, or I would say hallucinated, because here they are really hallucinating even because the right behavior is not to produce anything. So this came up yesterday, and I tried it the other day. I got the ChatGPT API. I fed a dialogue of between mother and a child. I told ChatGPT to be a child, and I fed the mother's data in line by line. This is what ChatGPT generated. The point here is not to diagnose what's wrong. The point here is that these models have not solved, everything. So my own work, goes back over 20 years, was built on the intuition I think is widely shared that when we learn, if you have a set of items, many of them do something, you want to say all of them do that thing. If relatively few items in the set do something, you just say, I'm going to memorize them. I'm not going to go wild on this, right? Because I have not seen sufficient evidence to make this generalization. This intuition is widely shared, right? And the question is, how do we make precisely how many would be many or many enough, and how few would be few enough, right? This is the work that I said over 20 years ago. And you will see it's maybe finally paying some dividend. So one of the things we should realize, if you think about good enough learning, is that if you look at language, you realize it must be a threshold. It cannot be anything else. Because one thing we said earlier is already, right? We have cases where the rule is not good enough. You just don't generalize. So there is a tipping point at which you go with it, and or maybe below that you don't. One way to think about this is to look at acquisition of vocabulary and acquisition of grammar. So yesterday the topic came up, namely the notion of individual variation in child language. There's a lot of effort to study individual variation, but at the same time, I was really glad. I was actually frankly shocked that in the question in the online chat, someone in the audience brought up Bill LeBeouf's observation of what he called enigma of uniformity. I'll give you the full quote later, but here's a study. I mean, this is toy example, but it's a real one. It's based on the longitudinal developmental data of 6 children from the Providence corpus that were recorded as children from basically as soon as they were talking, around age 1 to a few years to maybe 3. And these are the first 10 verbs produced by 2 children. Okay, so you can see they have 18 words altogether, but 2 of them are shared in common. So this is just a way of saying, if you look at children's early vocabulary, they're not very similar at all. You can run this now more systematically on the word bank data. It's the same thing. So if you look at the most frequent, the first 25, 50, all the way to 150 first verbs produced by the 6 children in the province corpus, for each vocabulary size, you have, 6, so 15 comparisons pairwise. You can see that with the first 150 verbs, there's only about half of them are actually shared between any 2 children. Yet at this point, the grammars of the children, as far as verbs concerned, are identical. They all know verbs go before, go before the object. They can all inflect the verb, right in appropriate way, adding ed or s or ing. They even make the same mistakes. They all say he goed. And this is what a quote that I wanted to highlight, right? So this is from Bill Labov, has been saying this for many years. Bill Labov, for those of you who don't know, is the foremost sociolinguist who study the how people use language at a community and typical settings with great details. Anyway, so here's what he referred to as the enigma of uniformity. He said the end result is a high degree of uniformity in both the categorical and variable aspects of language production, where individual variations reduce below the level of linguistic significance. So if you're in the same speech community, say Philadelphia, you learn the same grammar. I mean, some people know more verbs, some people know fewer verbs, but the grammar, and that's not the kind of variation that's above the level of linguistic significance. But if you come to the phonological, morphological, and syntax systems, they're virtually identical. This is the result from many decades of social linguistic research. So that's one reason I think it needs to be a threshold, is that learning cannot be dependent on particular items. So we may learn very different set of words, but if a proportion of certain words follow a rule, meet some threshold for me and as well as for you, then we have the same rule. Another reason it has to be a threshold is that learning is very often non-monotonic. This is a very famous example in language acquisition. Many years ago, many tears were shed over the so-called past tense debate, again having to do with the predecessor of large language models. So this is a figure from Steve Pinker, and so he was looking at one child's Adam's acquisition of past tense. So Adam turned out Adam was studied fairly extensively longitudinally until for many years by Roger Brown. This is from the 60s, but the transcript has been widely available. So Adam did not produce a single mistake when he was using irregular verbs until just before age 3, when he made the first error of over regularization. He said, "What that feel like?" Now, feel is clear enough from the input because adults don't talk that way. And importantly, Adam produced felt correctly before this point, but somehow he started saying feel, right? So therefore, you see a regression in his accuracy for his past tense acquisition. Well, this is, of course, taken to be the indication that ED is not productive. So that they can extend it to novel items. Of course, feel is an irregular verb. If you don't remember felt, can retrieve felt accurately, you would end up using ED, but only if ED has become productive already, right? So languages very often has this up and downs of development. So learning is certainly not monotonic. These are legions, right? So non-monotonic learning is extremely common in child languages. These are some typical errors that English children overgeneralize when they're young, but somehow get out of them when they get older. So I died him. Don't giggle me. I said you something. You should say I said something to you. And also I deliver you lots of pieces. So these are there are many examples of the sort. Bob Burrick, Steve Pinker, and many others have, Melissa Barrowman, many people have worked on these problems in the past. It also shows that there's going to be a threshold, namely you see enough regular verbs. This is intuition shared again broadly. There's a notion of a critical mass in the connections to literature, which is really the same thing here. When children have seen enough regular verbs to overcome the irregulars, then that's when the ED rule is produced. It's the same logic can be extended to other examples of language acquisition. So because I was not able to find anything suitable for various reasons, A, they're almost all maximizing, and B, they have too many hyperparameters, and it's not clear whether those hyperparameters have any psychological standing. So I decided to roll my own, and I won't give you all the details here, but the main idea is that you can decide to either have a rule or not have a rule. If you don't have a rule, you know some words. You don't have a rule, you just have to memorize everything. You can memorize a list. Okay, and you can retrieve from the list. In fact, there are algorithms that can rank the list by fairly accurately by frequency. So the more frequent items would be earlier on the list, so you can access them faster, capturing the frequency effects in memorization. Alternatively, you can say I have a rule, but with some exceptions. How do I represent rules and exceptions in a computational model? Well, the only way I can think of, maybe that's because I'm a computer scientist, is that you have to do this by the bunch of if-then statements. If a rule has exceptions, you have to list exceptions, and then you say else, you add a rule. So the logic here is that if you can memorize everything, you can estimate its time complexity of access. If you have a rule plus exceptions, then for all the words that follow the rule, they have to wait for all the exceptions to be checked off before you can access the rule. So what I'm proposing is that you wanted to take the cheaper option, namely the faster option. Okay, so this idea was put forward some time ago, but I was surprised to find real-time processing evidence in favor of this organizational nature of rules and exceptions in inflectional morphology processing. So long story short, I couldn't do the math, and I got a friend of mine, Sam Gutman, who's big in quantum computing, so this was very easy for him. He helped me prove the theorem or result, at least. That is that if we have n items in a set, some of them follow a pattern, some don't follow the pattern. This pattern generalizes if and only if the number of exceptions, namely those that do not follow the pattern, fall below the threshold of n over the natural log of n. So here are some values I can give you. So if you know 10 items, you can generalize if you follow, if at least six of them follow a rule, because here the threshold is 4. If you hit 100 items, you would actually need 79 to generalize, because here the threshold is 21. And here just give you some values of n and how many members are in a set, and what's the cardinality of the subset to follow the pattern, or you need to generalize. What's notable is that the proportion decreases significantly. So in other words, when n is small, when you're working with fewer items, it's easier for you to generalize than with more items. I should say this model is parameter free. N is simply the input value. You simply count how many items are in the set that follow a pattern. Then you make a categorical decision on whether you generalize or not, right? So you can think of this as some sort of a bifurcation. Now, as I said, this work was done over 20 years ago, but very few people believed it. I didn't quite believe it either. But over the years, thanks to the goodwill of collaborators and colleagues and students, I think this idea is beginning to pay some dividends. So one line of work, I won't talk about the linguistic problem because they're complicated, and this audience is not full of linguists. And one of the things people have done in the past, my colleagues and I have done in the past, really, they did this, is to create artificial languages and manipulate the ratio of exceptions and rule following items and see what children do. So this is a work of Alyssa Newport and Katie Schuler at Georgetown at the time. So in this study, I won't give you all the details here. Children see made up objects with made up names, and they have learned a plural ending, ka. You can see some of the items take ka, some of the items take po. So this is carefully manipulated. So some items take ka, that's a rule item. Some of them take po or t or something that's not ka. So what we found is that when you have if you teach children 9 nouns, if 5 of them share a suffix ka, The other four exceptions, children actually categorically generalize. Okay, and however, if you tweak this in the other way, namely 9 items, 3 of them follow the share the ending, share the rule ending. The other 6 are all idiosyncratic. You find that even though the 3 are by far the most frequent items children are exposed to, the dominant response is to say nothing. So I want to point you to this thing here, is to say nothing. Okay, this is really like a stridden. People just don't know what to do because you don't even know one of the rules is dominant is not good enough. So therefore, children do not generalize. This is done by because if you do the math, it's for 9 items, it's the threshold is 4. If you really need 5 to generalize, you cannot generalize with 3. The 5 or more to generalize. One objection people can raise here is that 5 out of 9 is still the majority. So can we push this model harder and further? And this is the work of your colleague here in Montreal, Ru Shenshi, who, as we know yesterday, did a lot of important work in acquisition of language, especially in early infancy. And this is, I'm just reporting the work they did. This came out last year. So it's not a really artificial language because it's a French learning babies, probably maybe some of the kids have no experience with Russian. So it's really a natural language, but as far as the children are concerned, this is just alien language. And it's also a passive learning, implicit learning paradigm. This is like playing with toys. This is playing in the background. And here's a crucial maneuver. The Russian is a free word order language. You can think of this as the word order can permutate fairly easily, at least for short sentences. So one rule can be described as you have a word ABC, the first 2 words can swap order, and the other one is ABC, the last 2 words can swap order. It sounds like this. I hope you can hear this.
Мачты гнутся луком, гнутся мачты луком.
That's ABC, BAC. And this is, I don't know what it means, but it means something Russian, I suppose.
Мачты гнутся луком, мачты луком гнутся.
Okay, so infants are randomly assigned to rule 1 and rule 2 in 2 groups. Within each group, there's a crucial maneuver. So all infants are exposed to 16 ABCs, but half of the infants were exposed to 11 out of the 16 ABCs, or where the first 2 words swap order. The other half of the infants in rule 1 group only heard 10 out of 16. Okay, so the question is, after being exposed to this kind of word order permutation, I wouldn't go as far as saying the word is simply pattern learning here, because this is not referential, as far as like we can tell, totally meaningless to the French learning babies. The question is that how many out of 16 do we need to hear to form a generalization? This is tested on a very typical preferential looking paradigm. So after training, you want to see, you give them a novel ABC sequence they've never heard before, followed by either BAC, which is the pattern they were exposed to, either 11 out of 16 or 10 out of 16, or ABC and ACB, namely the pattern from the other group they've never heard. They were never exposed at all. The question is that, do we get a differential between the 11 out of 16 or the 10 out of 16 groups? If children listen to if you find a difference in the preferential looking time, it means that they have detected a difference between either a pattern they were exposed to various degrees and a pattern they were never exposed to. And the results are really quite strong. So it turned out that they see 11 out of 16, they generalize, they recognize the novel patterns that conform to the pattern they were exposed to versus the one that does not. But if they only hear 10 out of 16 items, they don't. Well, this is good news for me, because for n equals 16, the threshold is actually 5. So really, it's predicted that 11 out of 16 generalized, but not 10 out of 16. So they really pushed this principle to the extreme, and it certainly didn't cut me any slack. In fact, they analyzed a bunch of other data from previous studies and try to show that is the behavior of learning is best captured by a threshold or step function or some kind of continuum. The answer is clearly a step function. So 50%, I mean, notice that this is it's not a ratio, because this ratio is not constant. It's really dependent on how many items in the set you're you're dealing with, because as the cognitive set goes up, the ratio that's required to generalize actually gets higher. So I say this is a grammar as satisficing. That is, grammar is always provisional. You have a rule, as long as it works well, namely the number of exceptions falls below the threshold, you're going to keep it. Okay, so the traditional view of a look at hypothesis testing, this goes back to the long tradition of hypothesis testing, is the idea that once a hypothesis is disconfirmed, is runs into an error, is rejected. Here I'm saying no, we don't need to do that. As long as the hypothesis is good enough, namely the number of exceptions is below the threshold, you keep it. Okay, so here we're not trying to get down to the absolute truth here. We don't need to over-intellectualize the problem of learning. The child isn't looking for a fail-proof hypothesis. The child is looking for a hypothesis that's going to work well enough in their ecological environment. As you can see, this can easily get non-monotonic learning out of the trajectory. All depends on the empirical composition of the data. If you learn 10 items, if 7 will follow a pattern, then you generalize, because 7 is more than 6. 6 would be enough. If you learn another 5, but only 2 follow the pattern, so you have 15 now, but you can't generalize, because to generalize for 15, you need 10. Now you only have 9, but you have learned another 5 items, you have 20. If all of them follow the pattern, you can generalize again. Notice I'm being very careful here in not using the word, you're not using a word, I use item or pattern, because I don't think this principle of learning is unique to language at all. In fact, Rushan and Emond's work show that this French learning babies exposed into this noisy pattern of Russian clearly shows this is not a principle that's unique to language. Well, how is this done? I have no idea. Okay, I was pleased this principle works as well as it did, but I have no idea how this is done, and how the threshold is actually calculated in a brain. At the same time, I think we shouldn't underestimate the animal's apparent numerical ability. And another thing is that this I found puzzling, is that there's some resistance of this idea, as if this kind of a ratio tracking requires such complicated computation that is infeasible. I don't think I'm saying anything new, because a ratio tracking is well documented in infant studies. In fact, in the transitional probability, which is probably the most famous study of statistical learning, amply demonstrates the infant's capacity for tracking ratios. If you remember, transitional probability is to track basic condition probability between A and B. So in their TP, their transitional probability is tracking, say, the transitional probability between syllables, 2 different syllables, right? So to do so, you need a token frequency of one type divided by the sum of token frequencies of multiple types. So for me, it's just a ratio of type versus type. So in fact, in almost all, I think, the transitional probability studies, by design, every type have the same token frequency. So as far as I can tell, they are tracking types. They're not tracking tokens at all. So this is something that we can discuss further. But I'm saying that as interesting as the results for the tolerance principle are, there's no need to be unreasonably skeptical about them, because this kind of ratio tracking is being amply documented in both language and also in non-linguistic domains. Now, I have no idea how the natural log threshold is calculated, but we probably don't even know how frequencies are tracked in the brain precisely either. So to summarize this, is that I want to say that this is a different kind of approach to learning The individual does not need to commit a choice if the supporting evidence isn't sufficient. So this is quite unlike machine learning systems where there's always a winner. And ancillary assumptions will have to be needed, I think, to suppress them so they don't hallucinate, as in the case I've shown earlier. And this principle also has a built-in regularizer to prevent overfitting because it tells you when you don't need to fit anymore, because you can always memorize. There's no psychological penalty for memorizing. We know humans and animals have a large memory capacity. And also has, interestingly, a built-in small sample bias. So it's possible to generalize 3 out of 5 or 5 out of 9 or 11 out of 16, but it's impossible to generalize 30 out of 50. 50 out of 90 or 68 out of 100, even though the ratios are the same. So I guess 70. So this favors, I think, language acquisition. This goes back to the comments, I think, yesterday, the idea that it's beneficial to start small, but exactly how? I think the benefit of starting small lies in the children's small vocabulary when they learn the language early on. So all the rules are going to be robustly tested. Boom, this principle will get you that. As opposed to if your children were to instantly learn 20,000 words, then according to this principle, no language can possibly be learned. I want to wrap up quickly. So this leads to an idea of learning by abduction. This is, again, a notion that featured probably more prominently back then, not so much anymore. So it's basically you have some data, you want to come up with some hypothesis over it, and you want to see it's good enough. You can use this principle to evaluate whether this hypothesis is good enough. You get more data, well, you try it again. If it's still good enough, you're going to keep it. If it's not good enough, you're going to move on to something else. Since Stephen here, so we can think of this as a very general principle for learning lots of things, including learning, forming categories. Again, the categorization literature, if you look at the computation models, again, laden with hyperparameters and ad hoc or post hoc choices. So here, I want to say that if there's a set of items, so here's 12 items, right? If many of them, enough of them, or 8 out of them of the same type, you're done. You have one category there, you have memorized 4 exceptions. But if none of the patterns is or defining features of these items is sufficiently homogeneous as measured by this principle, then you subdivide into subcategories. Then the search continues recursively within. I won't give you details here. So let's say this little problem can be viewed as you want to predict the shape and the number on the object, whether it can predict the color. Okay, you can set up this as a typical categorization or learning task. And this thing would invite you to go to say, what makes something blue? You collect all the blue examples. You see that whether the feature of being odd or even or being the shape is going to be good enough on the tolerance principle to predict blue. And then you have to collect all the examples. So here you say it's odd, because 4 out of 5 is fine by the tolerance principle. Then you have to collect all the items in the data set to see whether odd can predict blue. So 4 out of 7 here, good enough. So you really have a rule that says that if something is odd, it's blue. I have to memorize 3 exceptions. Otherwise, it's even. Otherwise, it's yellow. I do have to memorize 2 exceptions. So here, instead of memorizing 12 items by rote, you memorize 2 rules with 5 exceptions. And this thing can be carried out incrementally. If you learn another item, 49, a square, but it's red. Now the rule is broken. The decision tree of odd going to blue is broken because for n equals 5, n equals 8 now, you need 5 to generalize. 4 is not enough. So you go back and traverse up the decision tree. You do a repair, and you try some other feature. So in the end, you end up with a different tree, where the shape feature was invoked in order to classify the items appropriately. So now you have 13 items. You need to memorize 3 rules and 4 exceptions. Again, this is parameter free. So now I want to go back to why this language very often fail, although probably fail more often than people realize. So majority can fail, right? Because according to this principle of generalization, you need a supermajority in order to, to generalize. So here, again, why you can't say stritten or strode is because if you look at the verbs in English, although majority of them share the past tense and past participle, they're nowhere near enough for it to be generalized. So if you look at most relatively common words, you find 55% of them share the same form. All the others are different, but in order to generalize out of 95, you need there are way too many exceptions than can be tolerated. And certainly if you go to all the vocabularies, it's about the same thing. And this can get you non-monotonic decision trees, and I won't go into the details here, but these models of incremental rule learning for English, for German, and for Russian have been implemented. Not for Russian. We can sample vocabulary incrementally and learn a decision tree and revise the decision tree, updating the branches in how many words go for a branch, how many words go into the branch, go against it, and develop an incremental model of rule learning, and basically a more and more elaborate decision tree. We do observe non-monotonic learning, but if you train any neural model, it shoots straight up. There's no evidence of non-monotonicity at all. I won't go into all the linguistic details here. I want to wrap things up. Is that I want to recall a title of a well-known paper back in the 1980s. I'm sure Stefan had something to do with it. And I'm just old enough to at the tail end of that first wave of enthusiasm, I still remember coding up backprop when I was in high school. So how do we deal with the rise of LLMs? Well, one thing is, of course, if you can't beat them, join them. Another way, I think, which I favor, is to go back to the beginning and develop our own end-to-end system, which is really the goal of linguistic theory, namely the discovery procedure. We're going to take a corpus, we're going to get a grammar out of it. So I think I did take longer than I wanted. Apologize, but thank you.
Thank you very much. You don't have a designated discussant, so we have plenty of time for discussion anyway. Please raise your hands, or the panelists can intervene directly. And I'm going to actually ask Ronnie, who's going to be speaking next, but who might have something that he would like to interpolate at this point.
I can take one of the questions Q&A in the chat window. No, this is not a special case of MDL for many reasons. I did try this because it's sort of the obvious thing to do. One thing I want to emphasize that is true for both MDL and also for Bayesian models, that the representation of the rule and the coverage of the rule are jointly evaluated, right? Because the code, you need a coding scheme. You have to measure the length of coding scheme. Then you have to measure the data under the coding scheme. They're jointly optimized. So here, this is a view that the tolerance principle actually is a radical detachment of the format of the rule and its coverage. The fact that it is used for morphology, for phonology, for this pattern learning, as in Rushin study, shows that these things should be detached. So this is actually a total rejection of MDL, or any model that tries to conflate the substance of the rule and the coverage of the rule. Now the particular reason I did not pursue MDL is that MDL, the way it's practiced in this business is unprincipled, because if I want to, the reason I'd settle for time access time is because you can at least do experiments to see which word is processed faster. So there's some sort of a response, there's some sort of accountability on the metric you're invoking. But if you do for space, I have no idea how many cells or what's the independent measure of space for storing a word or for storing. We'll have no idea. I can make up numbers, but it's completely unprincipled. So it's another reason I did not go with MDL. But they're fundamentally different. It's a fundamentally different conception of, what Tom, in linguistic terms, the difference between formal principles and substantive principles. But it's an important question to raise, and that's something I did think about. The second question is, with building primitives, No, right. So this is a great point. So this zigzag kind of thing, you try to detect necessary conditions, and then try to turn this into sufficient, and then test whether it's also sufficient. When you do not find necessary conditions, you try to go direct to sufficient. So you're really trying to do these kind of a correlative mapping at the same time, and you use the same principle to measure the validity of those generalizations.
Charles, these questions were sent to you privately, so you have to repeat them.
Oh, I'm sorry. So sorry. The first question was MDL, about MDL. So the first question is, I suspect that the tolerance principle is a special case of the MDL principle. In particular, it does not take the comograph complexity of a rule into account. What's a reference? And I think I answered that, is that I think it's a mistake to conflate the complexity of a rule and the coverage of a rule, and then do some sort of a joint inference over them. The second, question is, the TP is evaluation metric with built-in primitives such as odd and even. Are there extensionally equivalent metrics to the TP? How do we know this objective principle is unique? How do we know it's necessary and sufficient, not just sufficient? Now, this is what I was beginning to answer, and this is a great question. So the tolerance principle itself takes no stance on what is a primitive. My former colleague, the late colleague Lila Gleiman, had a great way of putting it. She used to say, you see red, but not infrared. The fact that you can see red is part of your cognitive design. The fact that you don't see infrared is not, because it's not part of your cognitive design. So in some sense, on the one hand, I wanted to maintain the principle is neutral to the primitives that we assume. Of course, every time you work on a particular problem, you bring all kinds of biases. I hate the term bias. You bring all kinds of assumptions about the problem over which the principle can operate. And so in the case of language, I think this is really another reason why we need to go back to the discovery procedure, is that language make different choices when it comes to the primitives, even though all the primitives are probably universally shared. For example, shape is clearly a cognitive feature that humans automatically have access to, but not all languages encode shape linguistically. There are languages with classifier systems like Chinese that does encode shape linguistically, right? So the features have to be primitive, have to be available, cognitively available somehow, but whether they are invoked or not in any particular language is something you have to learn. And this principle would give you a way of learning it, right? Because if you have a bunch of words in the Chinese language that take a classifier, if you don't invoke the shape, which is the cognitive feature that's available to you, you won't find a rule. Okay, so this is a deep question that I don't have full answers, but I do want to take a stance that A is everybody's problem, and B, I want to maintain a separation between the primitives and a format of a rule and the evaluation process, the goodness measure of the process. For me, I think they're very different.
Okay, we have some other questions for you.
Yeah.
Before I go to Ava, Virginia mentioned, and I'm saying this out loud so that Rushen can hear, I have promoted Rushen to the panel a few times, but there must be some reason why she's not intervening. You are being invited to intervene if you'd like to. But right now it's Eva Portelans who has a question to ask, and then we have Hamid who has asked to ask a question as well. Go ahead.
Sure, please.
Yeah, hi, Charles. That's what I really enjoyed your talk. That was really great. I guess I have sort of a more open question based on these sort of closing ideas. So in terms of this discovery procedure in ML, we've actually seen some pretty big leaps in grammar induction models in recent years. And I wondered what your take is on using these types of models as a way to do this discovery procedure, and what you think, if these models are to learn a grammar over their language, say a PCFG or a categorical grammar or something like that, what is the role that they then play for linguistic theory?
Right. This is a great question. Let me answer in several parts, right? The way I was trained in machine learning, I think this is probably still a lot of people think about machine learning, is to define a class of functions and prove it's learnable, and or have algorithms that for learnable, right? And in some ways that coincides with that converges with the linguistic way of thinking about things. That define a class of possible grammars, principal and parameters, or OOT, then they have algorithms to learn them, right? I think that's a mistake. I think that's a mistake. I think we tried and it didn't work. I don't think it's plausible to come up with such a totality of functions that's well defined enough that you can have provable learning in results. What I wanted to see, I believe in what I'm doing, right? So this thing is an algorithm. So this algorithm will learn a class, we need to think about this, differently. So instead of defining class learnable functions, we define a class function learnable by an algorithm, and then see how that intersects with other or our cognitive, apparatus. So I think on the one hand, I fundamentally disagree with the way we used to do things, and I have not found a good mathematical framework to think about this way I'm thinking about things. On the other, I am familiar with the grammar induction models out there. And of course, some of the learnable, verbally, learnable classes of language are just not real languages. On the other hand, in a better defined domains of phonology, I'm thinking about Jeff Hines' work and so on, where they do have a very careful and I think empirically accurate I would say catalog or typology of phonological systems. They're typically finite state in some fashion. The algorithm have nowhere near the kind of connection to developmental data that we need to see to validate them, right? So in this tradition, I think I will point you to the work of Caleb Bell, a former student of mine from Michigan, now it's Utah, and he's really taking actual data of real corpus data in words and all, right? Because a lot of the formal learning models feed the learner pristine data. All the lexical exceptions are removed. You can't do that. And if you do that, you can never make connection to actual empirical studies of language acquisition. So Caleb's work actually takes a corpus, words and all, words that follow the phonological pattern, words don't follow a phonological pattern, words that need to be derived from a different underlying form from surface form. So I refer to a couple of papers by him in one in phonology, one in linguistic inquiry. I think that's the way to go.
Okay, there's a question in the open questions from QA, and I actually have a variant on that question to add. First, look at QA's question and answer it directly, and then I'll generalize it.
Right. Question: if you want to choose a class of algorithms, I don't, as I said, I don't have a good handle on this, right? I think I'm, dumb luck. I stumble on a procedure, a learning decision procedure that seems to be effective. I mean, for things I've tested, I don't know more than that. Exactly how this is situated in a broader mathematical or computational framework, I have no idea. I've been trying to get help from theoretical machine learning people. I have not been able to get very far. So exactly how to evaluate this tolerance, I'm completely open to suggestions and how to embed this in some other system, or maybe there's a deeper reason for it.
Charles, it was a mathematician who helped you get the logarithm ratio.
Right.
Why not recruit people who are able to take this problem on? It's a natural question. The notion of optimization, which is contrasted with satisficing, has been very well and deeply analyzed by quantitatively. There's no reason why satisficing shouldn't as well. And it shouldn't be linguists pointing to data from children. It's not an empirical question. It's an analytical question. With different sample sizes, under different probabilities, what are the, not the optimalities, but what are the whatever you call it, that work?
Right. So let me go back to the assumptions. So the reason the natural log appears in the equation was because I made an assumption that words follow Zipf's law. Right. And if you want to follow Zipf's law, you can estimate their probabilities by the harmonic number. And then to take another leap of faith, you can approximate the harmonic number by the natural log of n. But those assumptions are wildly wrong when it comes to empirical cases. For example, in Rushin's study, the 16 items are of uniform frequency. It violates the principle, the assumption of the principle left and right. Yet the threshold appears to stick. So there are a lot of things about this I do not understand. It's certainly the child is not tracking the empirical probabilistic distribution of the item, because they were tracking that, they will not get they will not follow the tolerance principle, right? So exactly what is, so I think there's a, when we talk about probabilistic distribution, we're talking about probability distribution in an external world, and how children perceive such events is, it may not be vertical. They may just, as I said, it may just be that they keep, if a type or word occurs often enough, it counts as one. If this item counts, even occurs a billion times, it doesn't count more. So I think there's some very big differences between what the data is like out there and how humans process, internalize the data. Kind of goes back to the E language and I language distinction. But I'm certainly open to help, and this is not a I'm certainly not territorial, about this. If anything, I've been trying to extend this work to other domains of cognition.
That's understood. I don't understand why people don't take up the challenge. This is not an empirical question you're asking. This is an analytical question. It can be done by simulation under different conditions. You can even, that's sort of semi-empirical. But there are other questions in the open.
Right. Julia has a really good question. So is satisficing different from greedy optimization? This is a long-standing question. So, and Simon made this point, and many philosophers and people in boundary rationality, businesses had made this point. People in decision making, people who favor heuristics versus other strategies have made this point. The notion of satisficing, it may be harmless to say that satisficing is really you're trying to optimize but couldn't do it because of the cognitive constraints. And it may be harmless to cast the problem that way. But there's a conceptual difference, and ultimately an empirical one, is that satisficing is that you don't even try to optimize. You just go there and you find if something's good enough, you stop. So one of the differences is that if you're trying to greedily optimize, the alternative hypothesis has to be postulated in order to be evaluated, even though you may not, because of computational resource constraints, you don't end up picking it or don't end up evaluating them fully. Another way, but there's very good evidence that when goes back to 1960s when people like Patrick Suppi's reacting to Bayesians, is that in many cases where the subject has not conjectured a hypothesis. There's no evidence that they ever entertained some hypothesis, and you're asking people to do optimization over them. That's not empirically warranted. So I do think this is a learning procedure that attains to as few, possibly even one hypothesis at a time, and rather than doing constant hypothesis comparison and optimization, it will change the mind when the rule or the principle is not good enough. Hypothesis is not good enough, but it's not this kind of a very computationally intensive optimization scheme that's constantly comparing and scheming, because the empirical evidence does not seem to suggest that even entertaining more complex rules when the simpler rule is actually sufficient.
I think this will also have to be brought up when Alyosha gives his talk on generalization next week.
Sure.
Now I'm just going to try to induce some comments from Carl. You're there. Do you have any views on this?
I'm forming the views. This is a learning experience for me. I'll just thank you for the opportunity just to comment. Several things caught my attention in terms of the convergence between some of the arguments we've just heard and how one might tackle this from the point of view of vanilla Bayesian inference. First of all, satisficing, I think, is a wonderful concept and is very close to minimizing the complexity of accurate accounts of data. which is, if you like, the objective of structured learning or Bayesian model selection, noting that the evidence is the accuracy minus the complexity. And from that point of view, the notion of satisficing, I think, is absolutely central to a certain kind of Bayes optimal account. So I found that very compelling. Do you ever talk to Gigerenzer, Gerd Gigerenzer?
I don't know him personally, but I know his collaborators and colleagues, and this is exactly the area. I mean, I've been going to. I mean, I spent 20 years doing 20 plus years doing linguistics. I'm quite ready to move on to something different. So on the one hand, I advertise this, but I don't think I have time for this. This work has been applied to decision making, to the formation of social conventions, on social networks and so on, and it connects deeply with decision making literature, because the same issue came up there as well. I don't have time to discuss this work. This is some recent work with a couple of other colleagues. But yes, but this is exactly the space of boundary rationality that I've been moving into.
Excellent. The other sort of phrases and ideas that
Sorry to interrupt. Sorry to interrupt. Charles, could you take off your screen sharing, please?
Oh, right. Okay.
Sorry, go ahead, Carl.
No, I was just there are a couple of other things which caught my attention, and this notion of discovery. Again, it's a word that is used very often in my field in terms of network discovery or rule discovery, and could also be read in terms of structure learning, which again is very closely aligned or can be implemented with Bayesian model selection. It's a really difficult problem, and it sounds as though you've been dealing with this really difficult problem for a long time. There are some sort of priors that you can use to finesse that kind of discovery problem that inherit from vanilla Bayes, like non-parametric Bayes, stick breaking processes that I assume have been deployed in the context of hierarchical Dirichlet models in language, but I don't know. That's my question. And the other thing, which is probably less prominent in the machine learning literature, is species discovery. The work of the great and good like Fisher and the like in the 50s, where they were trying to work out what's the probability that I'm going to discover a new species if I keep on looking on this new island? And then that begs the question, how do you categorize a species? Or is this an exception that now licenses the creation of a new species? So it just strikes me that there's some really interesting parallels in other fields that relate to this central notion of carving nature at its joints in the right way to discover the underlying structure.
Absolutely right. This is really thank you for your comments. The first thing I'm familiar with. I mean, those methods being used for structured learning in language by Bayesian methods being extensively used, and I don't agree with that approach, which is one of the reasons I developed this whole thing. The second thing is really interesting because in category formation, generally we're not informed by how many categories there are. And we are not informed by the hyperparameters, talk about density, talk about separation. We're not given those. And language actually offers a great way of looking at this. So this is, again, came up yesterday. People are talking about functional words. How do we learn them? And the languages that may differ in those cases. So this is a case where I've been doing this work and with language because it's easy. If you have a 10 words, if 6 of them are sufficiently are the same, or then you don't need to create a category. You only partition when the homogeneity has been punctured as measured by this principle. Then you say, I can't make sense of the data. I need to find some way to partition them. And that's how this is how linguistic rules are defined. Sometimes they're defined on phonology, sometimes they're defined by gender. And so language offers a perfect way of analyzing this. Now, we're talking about a human psychological process that presumably we all do. This is how we learn language and learn many other things. In the practice of species discovery, there's a normative aspect to it. But how do we juggle between the normative aspect and the descriptive aspect is something that I think is really interesting to look into. I've been doing some work in reproducing the classic studies in category formation in psychology by applying this principle. But this is, as I said, I'm perfectly happy to apply this everywhere.
Thank you.
Thank you.
This is Serge Robert here. I'd like to comment on the difference and complementarity between non-monotonicity and abduction. In my studies of human reasoning, I think I reached something that is close to what you're saying. And the idea is that non-monotonicity is a family of procedures by which we stop using a rule, considering that new data tells us that the rule is not good enough anymore.
Mm-hmm.
And the abduction procedures are the procedures by which we try to switch to a new rule.
That's right.
We modify the rule in order to take into consideration the new data. Mm-hmm. And in my studies of human reasoning, I reach exactly the same conclusion. That is, the dynamics of human cognition is much something that goes from abduction to discovery of new data, and this way applying non-monotonic procedures, and then try to reach new abductive rule. I'd like you to comment on this, please.
I completely agree. I mean, so one of the things that I was a student of Chomsky's, and I'd been doing linguistics for a long time. For a long time, I thought, as many linguists thought, was a language that was different. And language, is different. I mean, it's different from lots of other things. And there's certainly a substantive hierarchy. We don't need to go into there. But I think that sometimes we think the substance of language is also different. So now, because of my struggle in trying to come up with a good learning principle and having stumbled upon this thing, now I'm beginning to see that it's not language is different. Is everything else is the same. So they always, again, it calls upon us to develop a principled procedure, a learning procedure or evaluation procedure, however you want to call it, and try to apply it to other domains. So I think this actually is what Chomsky has been saying more recently, is to bring the study of language closer to the rest of cognition and biology. And I think, but in order to do that, of course, the facts of language don't go away. We used to think they were all big, all baked in, but now we're saying it's learned. But in order to come up with the right learning procedure, it's very difficult. I mean, this is why, if a proposal like this is going to take a long time for people to accept it. Right. But I think we're getting there, and more converging evidence from other domains to support this view, the better.
Yeah, I agree totally. I think that's the most important thing that cognitive science has shown us compared to the logical empiricist tradition in which people like me have been raised years ago. Thank you so much.
Thank you. I'll look up your work.
Look at the prior summer school, which was
okay.
2016.
2016.
Yeah,
okay.
Well, we did on recent.
Actually, did you have all of the videos for that too, Serge?
Yes. Most of them, not all, but most of them.
Good. Now,
the most important ones.
We're running out of time. Are there people who have? Oh, I should do my usual challenge to the present audience. Now the mantle falls on you. You can do any emperor's new clothes, or I have no idea what you're talking about. You can intervene now to bring us all back to reality. If you haven't been following this point by point, come and say so, and we'll try to compensate for it. Yesterday, this worked in the panel session. Are you all mute? Okay, do it.
Thank you, Bert. Okay, I didn't grasp all of it, but trying to follow up on Serge Robert's ideas of abduction as a better rule forming, meeting new data, and trying to expand on the concept of satisficing. The work Herbert Simon did on bounded rationality was mostly, as I understand it, computer science thinking and behavioral system thinking, but trying to satisfy the lack of control over issues of friction and industrial production in the context of Cold War. So it's classic thinking and decision-making theory, but trying to give it a broader view with language and generalization. Can you expand a bit further on the concept of the non-monotonous decision tree? How that would work? So that would be the kind of formal reasoning that we set in place to mimic how children try to figure out the irregularities and the linguistic phenomena, escaping the strict rule following. So if you can expand a bit on the non-monotonicity and the decision tree.
Okay, so that's in for English past tense, right? That's a particular case of non-monotonic learning, and that's entirely due to it's an empirical effect of the English words and their frequencies. It's well known that if you think about it for a second, the most frequent verbs in English are irregulars. So because children learn the more frequent words first, if you look at the first 50 words, more than half of them are going to be irregulars. So less than half of them are going to take ED. So there's no way by the principle, there's no way for the child to generalize it. It really has to the monotonicity arises so they're in that stage they just memorize. So because they're simply retrieving items from memory, they won't make mistakes. Mistakes only come in when they learn enough regular verbs to overcome the irregulars. As I said, it has to be a super majority. And that's when the ED rule became active. Then children start to now, of course, they fail to retrieve an irregular verb accurately. There is a bad rule to kick in, so those errors would begin to appear. So the point here is, and that can go back and forth. Entirely is the empirical composition of the words in the memory, in the lexicon, that go for a pattern or not go for the pattern. As I said, when I say words or pattern, I'm completely neutral. It could be any distinguishable types, items, and any kind of mapping or systematicity can be evaluated in this way. So the fact that in some cases of language learning, we have non-monotonicity is nothing particular about language, about learning. It all comes down to the empirical composition of the data. There are cases where there does not seem to be a clear case of non-monotonic learning. For example, English plural S. The reason is that even though there are irregular nouns like men, men, child, children, sheep, sheep, and so on, there's such a small minority of the nouns in the English language. I think I counted of the most frequent 100 nouns, only 6 are irregular, but of the most frequent 100 verbs, 55 are irregular. So for children learning the plural rule, and they learn 10 words, 20 words, S is already going to be the productive majority, right? So in that case, you may not see a non-monotonic curve. So it's entirely down to the empirical data, right? So I'd imagine this is the case in other domains of learning and reasoning. If the data is so crisp clear, you learn it instantly. No, you won't find any non-monotonicity. So there's nothing intrinsic about language learning that has to be non-monotonic. The monotonicity arises from this particular decision procedure that requires a certain threshold of a majority. And so when this is deployed in different domains, you get different learning trajectories. When you look at a large language model, it seems to be, it just gets better and better, with more data. I think the reason is if you look at in the cases of morphology learning, and we can train neural model for them because that's the biggest machine I can afford. They are really just matching the frequencies of the existing forms. That the fact that there's always going to be some form is more frequent or better by whatever measure is going to be the form that's produced. So you don't observe non-monotonicity, which is one of the reasons that I don't think large language models or dominant machine learning models is the right way to look at learning.
We have a few seconds left, a few minutes left, but finally, Rushen has raised her hand. Can you do it directly, Rushen? Go ahead.
Hi, Rushen. Thank you for coming.
Okay. Do you hear my
Yes,
voice?
yes.
Sorry, I had computer problems, so you can't see me except my name. Charles, I have a question for you. So we've seen with all these experimental data with children, adults, babies who show tolerance threshold. What's your take on machines? So if you have a language model and obviously tolerance principle favors smaller vocabulary, smaller number of items. And would you predict a language model network to do the same kind of, excuse me, to do the same kind of learning and succeed? Would you need to input the tolerance algorithm in there? And let's suppose a machine learns with a small number of samples and exactly like humans, like what your tolerance principle predict. What do you say about does that constitute evidence that is distributional learning? We don't need anything, UG, that even the machine, even say nothing endowed cognitively, especially for tolerance principle, it's just there. Any learning machine, human, even animal would work out as long as they will learn rules, as long as the data is okay for tolerance principle.
Excellent question. Excellent question.
Okay. Well, if $1 million, I guess you have to more than $1 million, $100 million. I would actually try to do this for real, to get data and to really faithfully implement the discovery procedure the way Harris and Chomsky envisioned. I would certainly bake the tolerance principle in. I don't think this is something the machines can self-organize in discovering it. I don't think that's possible because by design, those machines are maximizing machines. Right? So this principle has to be baked in. Now, what's left for universal grammar? Definitely merge, definitely hierarchy, definitely the notion of a head, and definitely the notion of categories. Categories, of course, is not unique to language, but I think for language, you definitely need merge and hierarchy. I can go on and on about some other linguistic problems I've worked on where the notion of a head of a projection is critical. But other than that, I mean, of course, that has to be intersecting with human cognitive apparatus. But other than that, I think I'm fully on board with Chomsky's more recent vision that merge is all you need. And we just have to let the learning component to do the heavy lifting and be really responsible about it because we have discovered lots of facts in the past 70 years, and they all have to be accounted for.
Okay, I want to thank you. We've run out of time, but the next session will be with Ronnie Kassir. We'll continue along the same wavelength. Thank you for.
Thank you, everyone.